Good afternoon and welcome to Webinar Wednesday. Thanks for joining us today for our presentation with James Freeman, multi-vendor modality manager with more than 38 years experience developing and delivering service training for CT and MV equipment. Webinar Wednesday would like to thank our sponsor, AllParts. AllParts Medical is a leading provider of medical parts, training, and technical support. AllParts supports most major OEMs, and in addition to parts sales, AllParts also provides customers an extensive array of in-depth training and technical support before and after the sale. An ISO certified quality management system helps deliver an industry-leading warranty rate. For more information, please visit allpartsmedical.com. A few announcements before we get started. We'd love for you to join us for continuing education, networking, and vendor engagement opportunities at our HTM Mixer coming up on September 9th and 10th in Kansas City. Please visit htmmixer.com for details, registration, and details on how we're making sure your meeting environment is safe and clean. While you're there, please make sure to sign up for our newsletter so you always have the most up-to-date information. Let's give one lucky attendee the opportunity to win a Webinar Wednesday shirt by answering the following question. AllParts provides parts from its 80,000 square foot facility in what city and state? You can find the answer on our sponsor's website, and please answer the question by using the question feature in the GoToWebinar dashboard. As always, today's webinar is eligible for one continuing education credit from the ACI. You can obtain your certificate by completing the post-webinar survey. More details will be at the end of today's webinar. We'll wrap up today with a live Q&A. You can submit your questions at any time during the webinar by using the question feature on the webinar dashboard. We'll get through as many questions as time allows. As I mentioned earlier, our speaker today is James Freeman. James, you may begin whenever you are ready.
Thank you.
Hello, my name is James Freeman, and I'd like to do the introduction to CT for you today. Our agenda will be a little bit of my background with regards to working CT since 1983 time frame. We'll go through a description of computerized tomography, the functionality and system components, the advantages over traditional radiology, which was considered traditional RNF and X-ray rooms. System overview, how images are made, image reconstruction process, just a rough background on that. Common issues that we see as CTs, aka high expensive parts, things that we see with regards to the most exposure to problems as well. And that directly impacts our service, our cost to serve, elements to consider when we do a service contract on CTs, what we look at as enablers to allow service for independent ISOs and third-party individuals working on the other OEM's equipment. And an enabler in this case would be the new Dunley DA200 P40 liquid bearing tube, which allows direct service with the GE Revolution EVO product line. And then we'll also talk about CT support at AllParts with regards to parts, Xray tubes, and training as well for independent organizations. So that's the quick agenda review. I started in medical imaging in 1982. In 83, I started with CT products. In the late 70s, I worked on radar and F4 FEMs as electronics technician and enjoyed my time in the military. Then later on, I've seen family and friends need to have CT scans. So direct involvement with regards to personally even being scanned on a CT scanner that I worked on. So my experience with CT has been both professional and personal. With a lot of my friends, not understanding exactly what an engineer does on CT products and the challenges, but at the same time understanding the importance of what we do and how we impact other people's lives has been somewhat of a driver for me with regards to how we can impact lives that we don't even know. So at some sites, I actually installed the very first CTs in the early 80s that the hospitals had. So saw how radiologists and hospital staff viewed CT as an enabler with regards to just patient care, especially in more of the rural areas where significant needs were needed. I worked with a mobile CT company that actually traveled to different sites, which allowed them to have a certificate of need based on the number of studies they were doing. So I can say that it's been a fruitful career for me, that I can see how I've impacted and improved other people's lives, and at the same time received a little bit of myself as well. One of the friends I had was a physicist, so one of the first CT scanners I installed in a local town, he, after hours, and I would go through the scanner, and he gave me more of a physics background of what he was testing and why he was testing, and I showed him a little bit of how we worked on the machines as well with regards to how the technology worked and the software ran and stuff like that. So it was very encouraging both ways. So computerized tomography, where is it used? Primarily hospitals and clinics. What it's used for, emergency and urgent care. With regards to the hospital's trauma center rating, CT is one of the devices that its uptime is an enabler for that trauma center rating. So with regards to CT, one of the first CTs in the market was a head-only scanner to image brain. So what CTs brought to market was the first system or modality to actually image brain, seeing brain tissue independently of doing other procedures. Along with that, that enabled neurology. And then later on, as whole body scanners like the one that you see on the picture here, enabled us to do basically whole body, which included the heart and the lungs, everything else as well. And then obviously the abdomen and pelvic area. And another opportunity that CT brings is very good anatomy location within the body. So with regards to radiation therapy planning, RT mentioned here, is that we could scan a patient and then put markers on different parts of your body and then relate that to the location of anatomy within your body. And then they can do better planning for radiation therapy. So the really enabler that CT brought to market was to be able to scan brain tissue. And then later on, obviously, as whole body scanners came to market, was basically 3D imaging. Most images that you're used to seeing are more what we would call an axial review of the data. But as you can tell with this CT scanner we're presented here, the table advances all the way in. And as we rotate around, inside the gantry would be a rotating assembly. We'll see that in the next following slides. But we create a volume of a cylinder as the patient's being scanned through, and the scanner rotated around the patient, a cylinder of data. And that cylinder of data allows us to reconstruct the data in many different directions. And the next slides will represent that. But one of the things that we have is a scaling system. And Dr. Hounsfield led a team to develop CT in the mid to early 70s. And Dr. Hounsfield's team in England, being with EMI, issued the first CT scanners in the English market, and they were head only. So one of the things that a scaling system needs to exist is when we scan, you have air around the body in that cylinder of data. We also have body tissue, either calcium, which is in our bones, our air even in our lungs, and then blood, obviously, and other materials. So we have to be able to reproduce that with regards to a CT number, aka Hounsfield number. So now they're called CT numbers, but technically they're still Hounsfield numbers as well. So the scaling system that we use is air is a -1000, and bone is, or calcium is in the high +900 area. and water being the center of the scale. But it's not any kind of water, it's distilled water. Distilled water, whether it's in Australia, Japan, the United States, Russia, or any other country, will have the same value. So it has no mineral content or anything else, it's just pure water. Pure water has a CT number of 0, so that's the center of our scaling system. And if you think about it, most of our bodies are made up of water. All the soft tissue is a component of water plus some other item. So with regards to dose or radiation exposure, CT scanners, obviously, as you can see, an X-ray, chest X-ray would be about 10 milligrams here, and they show a head CT would be about 150. But if you think about the head CT, we rotate it around the patient a minimum of 180 degrees to produce an image, but normally 360 degrees around the patient. So as we're taking that 360 degrees view, we're basically more efficient with our radiation, because if you took that X-ray, chest X-ray is only one exposure at one direction or 1 degree of angle, and we're going through 360 degrees of angle with only 150. That's actually a significant improvement. Okay. So examples of CT images that we talked about before with brain tissue. So that's our first slide. So we typically can look for tumors, calcifications, hemorrhages, bone trauma. So one of the things that we talked about here is that in the CT scan, we can scan you one time with that volumetric data. We have that data set now known as raw data or scan data. And that data we can process as with different algorithms. So one algorithm we call soft tissue algorithm differentiates and shows small changes in CT numbers, and we can use that to differentiate small CT numbers in the brain tissue with regards to what we see. So example, average brain tissue normally is a range of about 38 CT numbers plus or minus about 15 CT numbers. So representing the grayscale, we can do what we call window leveling, where we adjust the grayscale to represent the CT numbers so that we have a visual image from that. And here we're enhancing that image to view the soft tissue. CT was the first modality to be bringing this to market in the late 70s, early 80s. So the impact of CT obviously made a big difference in the marketplace, hence the trauma center rating as well. But with regards to this, if you notice now, we talked about how we can look at different structures, soft tissue. Okay, we can see if you have a bleed in your brain. An example would be a car accident where someone may have hit their head and injured their head. If you have a hematoma or a bleed, we would use a soft tissue algorithm and process the data. We could see that small change in CT numbers represented as maybe a displacement in the brain tissue or the bleed into the brain as well. That would also be an example of a stroke. But with regards to your skull, that we would use a bone algorithm, and then out that algorithm, we would be able to see fractures in your skull. And all this could be achieved with one scan and processing the data in 2 ways to produce 2 different data image sets. Okay, so that's the advantage of computerized tomography, is the processing power that we have in the computers to actually reproduce these images with different algorithms. So an example here is the chest, right? Pulmonary CT. So we're looking at lungs here. In this case, and you can see the bronchial tubes. The bottom left image has false color assigned to certain CT numbers to better enhance the data. And if you look at the images on the top, you're looking more at the heart with axial slices. So the aorta and vena cava coming from the top of the heart in the center and the bottom of the heart. And then you can see the heart muscle itself surrounded by the lungs in the image on the right top. So very concise. So image quality and image resolution is very important for us as engineers to properly align the system, make sure the equipment is functional and calibrated properly. to be able to produce these kind of images and affect people's lives in a positive way. Another example is cardiac imaging. So there's a little bit of difference with cardiac imaging. Instead of rotating around the patient and collecting data in 180 or 360 degrees continuously, we do it in segments. So we'll gate off the ECG, and that certain phase of your heart, different valves will be open or closed, and we will gate and then collect a little bit of data during that gated phase. As the gate will continue to rotate around, then we'll get the next gate phase, and then we'll collect some more data. And after we accumulate enough data to process an image, at least 180 degrees, hopefully more, we will see phases in here. So if you look at the example of the image on the right, midway you actually see a valve that's open in one of the valves of the heart. So that's what we can do with gated studies. So you can see also calcium and other things as well, depending on which window level numbers we see with regards to a heart. The image on the left is a 3D construction of a slice that's changed direction, orientation, but we also false colored based on CT numbers. So you can highlight areas of CT numbers with colors as well on the newer systems. So what's the advantage of cardiac CT over traditional angiography? Well, one is they used to have to stick a catheter in your leg and inject iodine, those kind of things, in a specialties room, which would obviously required you to be sedated, take the doctor, the radiologist doing the procedures to really just to do exploratory. In this case, now we could do this with a CT scan, not have to do anything with the doctors related to it unless they review the images afterwards. So once a problem is identified with a CT scanner, then those patients can be dealt with regards to the specialties room. But patients who did not have a problem, but something else may have been the issue, are identified, and then less other diagnosis are done with them. So it saves time, effort, and people who specifically need procedures now are going to get them, and other people who need to be eliminated due to other health issues, but to other procedures would be moved on. So in case of the abdomen, you see the liver outlined here. Almost every one of these tissues has a different density in the soft tissue, which means they're going to have slightly different CT number. So normal CT numbers that technologists see when they scan patients versus abnormal, which would show up in images at different CT numbers. So we can actually put a cursor over a given part of the anatomy, and the software will then show us on that cursor or within the bounds of that cursor CT numbers. And so that's called a region of interest. And we can look at the mean CT number and the standard deviation to know what those tissue CT numbers normally should be and what they're not. So we can do it both mathematically, and we can also look at it from a visual perspective as well. So CT brings a lot of accuracy with regards to actually the density of materials in your body as well. Not just how they look, but also assignments with regards to the water scaling system that we use, our Hounsfield CT number scaling system we use. So also lumbar spines, backs, thoracic spines, all these things we can see with CT as well. You can see where maybe a disc would intrude into your spinal column, and then pinched nerve give you a sciatica or other back problems as well. So CT is very good at this. And additionally, going forward, when MRI came to market in the mid to late 80s and early 90s, MRI could be leveraged as well. So you'll see either CT scans or MRIs used for some of these studies as well with regards to soft tissue. So general CT overview, we have an X-ray source, which in this case is Xray Tubes. So we produce radiation with it, but as long as we produce high voltage, then we have MA, our electrons flowing inside the X-ray vacuum tube, that produces X-ray. As soon as we turn off high voltage, we no longer have X-ray. So it's very controlled. It's not radioactive in any sense, but we do create radiation only when We bring up high voltage with current flowing through the tube. And then we have a collimator, aka beam fan control. That's the output port of that X-ray tube. And represented here in that light green is actually the beam profile as it passes through the patient and hits the face of the detector. The detector converts X-ray photons that hit a crystal. The crystal then radiates visible light or infrared light, depending on the detector design. And that then is picked up by a photodiode. And the photodiode then is converted into a mathematical number. It's called A to D, analog to digital conversion, in a data acquisition system. Siemens, GE, and Philips, and Toshiba all call them slightly different names. So it's called, if you notice, DAS here, DAS. That's an acronym that Toshiba, Canon, and GE use. And then Philips and Siemens uses the word DMS, Data Measurement System. Essentially the same, but we have different acronyms based on who the manufacturer is. So with regards to how images are made, so if you look at the center bottom where it says 128, that's the original image that you were trying to scan the patient, or in this case, 2 cylinders. If you look at image number 2 where it shows 2, if you take that data and you push it vertically and horizontally, you would see these squares represented with the data. Now, so that would be considered 2 views. So if you take the X-ray profile that you saw before and you projected one straight down, you would see number 2, you'd see the vertical lines. Then if you move the X-ray tube and detector to 90 degrees and shot through, then you would see the other data set. And basically what this is they would be on the edges. On the top, you might have one, and then on the left side, you might have the other. And as we push that data through a matrix, in this case, maybe a 512 by 512 matrix, and push the data across, as the data overlaps in that matrix, we produce these squares. Now, if we take more views of the data, in this case 4, so now we're taking and multiplying, rotating around at 4 positions around the patient, we get this data. The next one would show 8. And notice as we have more and more projections from more and more angles, we basically build up an image. So you see 16 is better representing the data set already. And then you see 128 in the center. That one we'll get back to. The one with no filtering, we basically that's what we would see without an algorithm applied to the data set. You see a little bit of ghosting because you get extra noise in the image, processing noise. And some of the noise is actually coming from the A to D conversions where you have a little bit of drift, those kind of things. So we get this foggy with no filter applied. So all CT scanners will apply a filter to the data set, a default filter or one that the technologist will assign as well, or multiple filters if we want to process the data to enhance different image data sets from the patient, like soft tissue or bone, or other ones as well. So this process is known as filtered back projection. So we're back projected the data into basically a void, a 512 by 512 matrix, or in the newer scanners, a 1024 by 1024 matrix. And we're pushing the data back through, and as that data accumulates, we're building this image. And then post-processing, before we reach the center 128, we would take the non-filtered data and then process it with a filter, a standard filter, bone, soft tissue, and then we would have more what represents the bottom image in the center 128. So this is kind of a generic view of a CT scanner. In this case, a 3rd generation CT scanner. The first 2 generations were very slow in acquisition. The first CT scanner that I ever worked on was a GE 8800 in 1983, and then it was considered a 3rd generation scanner in those days. The X-ray tube and the detector both rotate around the patient. 4th generation scanner, only the X-ray tube would rotate around, and then on the fixed circle, there would be detectors all the way around. That's very cost prohibitive when we get into multiple rows, where instead of just having one row like we did with early CTs, we have up to 64 to 128 to 256 rows now. The more detector elements you have out there, the more expensive it will be to have a 4th generation scanner. So if you think about you have an iPhone like an iPhone 5, and now you get an iPhone 12. The difference in those systems is that the memories have been improved, processing power is faster, those kind of things. But the topology, how the phone works, is no different. When we talk about generations and CT scanners, the functionality of how that scanner collects its data is fundamentally different. So one's not necessarily better than the other, they're just different. All current scanners in the marketplace are based on the third generation topology design. Okay. So as we move over, we see the X-ray controller. We call that X-ray generator nowadays in CT, and also X-ray rooms call them X-ray generator as well. So it works in conjunction with providing high voltage DC to the X-ray tube and filament control. Like if you think about a conventional light bulb where the filament would light up, we control the temperature or the amount of extra photons produced or electrons produced by that filament heating. So that's called MA control. So we control that with the X-ray generator, and we deal with high voltage. So when we say high voltage, we're dealing with up to 140,000 volts in conventional CT. So with regards to that, sometimes we'll have a negative 70,000 volts that we put on the cathode side and a positive 70,000 volts that we put on the anode side. So our total potential is 140,000 volts. CT scanners will go down to 80,000 volts, 80 kV. So we will talk about that. With regards to table, remember we're moving the table in and out and vertically rotating the table to center the patient. So the center crosshair you see in the gantry here, item number 24, is known as isocenter. That is the location in the gantry where you have the best image quality, the best resolution. And as things kind of move out from isocenter, things will get a little bit less, the resolution will degrade slightly. And when I say slightly, it's very, very minute, but it does happen just simply because of your isocenter having the best image resolution possible. Okay, so we have a gantry controller that rotates the gantry at a given speed very accurately, and then also triggers we're working with the computer in this case to the DAS to acquire data. So as we rotate the gantry, we get triggers to sample our collective view of data from each angle, and then the DAS is collecting and converting that data and then forwarding it to the image reconstruction process. In this case, it would be our scan data disks, our raw data disks that we would call disk drive array that would get the raw data, and then we would process that into a final image, and that final image would then go to the computer and be saved in today's market as a DICOM image, so the operator could view that image. So we would have mass storage that would be typically now DICOM server somewhere in the hospital network. But with original scanners, that actually was extra hard drive space or other hard drives that would save that image data, so you could view that as well, known as process data. So here's a higher detailed version of a CT scanner, in this case a GE-VCT64 slice block diagram. As you can tell, the host computer and its processing is all on the left side of the image here. And then we see on the very top of the block on the right is a table control to move the table up and down. And we have touch switches to drive that. Also, we have safety interlocks that keep the table from hitting the gantry. And also, if a patient is interfering with travel, there's a safety switch there, or tape switches we call them, to prevent that travel and injure the patient. Then you see the next area called TGPU in the center. That is controlling the stationary side of the gantry and also interfacing with the table to move the table and also advance the gantry rotation, axial drive, dealing with fans, a number of other things that are locally happen. And then we also have at the very bottom you see LSCOM that has to deal with communicating to the stationary part and to the rotating part of the gantry. Then on the rotating side, you see the onboard rotating processor, we call it ORP. This is receiving the signals over the slip rings. And then on the rotate frame, we see the X-ray generator, the X-ray tube, the collimator, and then the DAS. And then we see an output bound data set that comes off the very bottom, fiber optic to transmitters, to receivers on the slip rings, into what we call a VDIP or the DAS interface processor that receives the raw data. And then you see the disk arrays and processing takes place from there. So represented here is the gantry that we have at the AllParts office is a GE-VCT. And then you see more of the communications diagram listed from that hardware that you saw on the prior slide. So we have the host computer that will then send commands over Ethernet to the TGPU. The TGPU will then split those commands into functions appropriate for the table and the axial rotation, and then also pass commands through communications over the brushes to the onboard rotating processor computer, which will then split into X-ray control and collimator control, and then eventually to DAS control, number of views we're going to sample, the type of sampling mode we're going to be in, the aperture size, as well as the beam control for the collimator. So once the DAS collects the data per view basis, it will transmit. In this case, 32 rows go on one channel and then 32 rows go on the other channel over the slip rings through our communication rings to the receivers, which then wind up in the DIP, aka DAS interface processor. On this operator control, we have the GOC6 console, which is used on a VCT. In the case that you see here, we have the host computer obviously on the right, and then the DIC computer is the computer that receives the DAS data and then processes it. Also with the assist of the Verb, which is the second computer used for advanced recon, we have that. The scan data, a raw data, is saved in the high-speed disk array at the bottom. That is processing, used to process this raw data into finalized images. The DIG then sends the completed image to the host system in the DICOM format for viewing the patient data. So X-ray tubes. We typically see X-ray tubes fall in the category of about 2% efficient. So that means 98% of the time we're producing heat. So one of the design changes early in X-ray tubes was to have a rotating target so that the energy of that heat would be dissipated across the surface of the target. So the area of interest that we're concerned about is right where the blue beam hits the target and produces the purple X-rays in this event here. So as you can see, the hot cathode filament, we control the temperature of that filament. And in those changes of controlling the temperature, we control how many electrons are produced. And that controls how much current's flowing through the tube and how many X-ray photons are produced. So the high voltage accelerates that the electron beam from the left here, in this case, to the right, which is the anode. So we'll have a potential of up to 140,000 volts. In the case of CT, we use these tubes. You know, tube life is somewhere on the average of anywhere from 22 months to about 28 months in life. Each site will be different, but I consider them printer cartridges because eventually they will run out and you'll have to replace them. In the case of the X-ray generator here, over on the far left, you'll see high voltage DC, anywhere from 540 to 680 volts DC. That's called our DC bus. That drives over to the inverter, which controls changing it into AC. So those inverter controls will then generate AC to drive the high voltage tank to create DC. In this case, this tube uses one high voltage cable, so we're doing a potential of 140,000 volts on just the cathode side. Anode side is grounded. So the area of challenges with regards to high voltage, when something degrades, it could be either in the tube or the high voltage tank. We would consider that a high voltage arc, and sometimes trying to determine whether it's a tube related arc or the high voltage tank itself causing the arcing, we have to kind of break the system down during troubleshooting. and also the connection of the high voltage cable into the high voltage tank. In this case, that connection can basically degrade, and we have to make sure that it doesn't have any air around that connection. So the detector, right behind what you would see is a light seal plate here, is actually the detector elements, which are the crystals. So there are individual crystals. In this case, this detector has the depth of these cards right here, 64 rows going straight back. And each one of those has a separate detector element, aka crystal, feeding a photodiode, and the photodiode then feeding the A to D, which is on these circuit boards. And then A to D then is converted, obviously to a digital number, and that is then transferred to our data collection hard drives. So that being said, as you can tell, there's 50-row detector module detectors here, but 64 depth, and they represent about 768 channels total across this array. So for one view, we do a total sample of everything here and realize that we do 968 samples per rotation of 360 degrees. So that's almost one sample per third of a degree that we're moving all this data through at such a high rate. So common issues we've identified as X-ray tubes, just because of the expense, but also high voltage, time, and we talked about the rotating the anodes, so the bearings in that tube will wear out due to just aging out and being conventional ball bearings as well. The other risk items have to deal with high voltage as well, and that is the high voltage tanks themselves can produce arcing, and the inverters that drive them at these power levels can also fail. So we see a lot of challenges with regards to these parts degrading over time as well. Then on the opposite end, where we do the control, reprocessing data, we have the computers. So used for scanning, used for image reconstruction. They're used on individual boards on the subsystems. And then we have hard drives. And hard drives are operating, 10,000 RPM to 15,000 RPM 7 days a week, 24 hours a day, as the system is just sitting there waiting to be used. Then we have the detector modules themselves. Crystals are part of the detector module. We talked about that earlier, where the X-ray is converted by the crystal into a light, whether it's a visible light or an infrared light, and the photodiode picks that up and then converts it using the converter boards to A to D, our digital values that we then transmit to the recon computer hardware. Crystals and radiation are not friends. Crystals will degrade as exposed to radiation. So over time, detector module will degrade and then at some point in time fail in its life. And then those can be replaced as well. And then we have to deal with the gantry, axial drive motor spinning, whether it's integrated to the gantry or a separate motor and belt driven, and the amplifier that drives that. And then we have patient table errors that will be part of the challenge as well. Sometimes, in a lot of cases, it's the tape switches, because as they move patients in and out on gurneys, they will tear a tape switch, and that interference switch will then be open, and the table won't be able to run. The other is the element that drives the table in and out of the gantry that is being used quite a bit. And so over time, we'll see challenges with bearings or motor drive circuits for the table as well. So service for independent distributors with regards to reviewing service agreements and the like, is that we see customers not always going with OEM service, using third parties or independent service companies to do service. We would call this multi-vendor service. And with these goals in mind, we have to have a weighting of what we would look at as a cost exposure. So in the case of CT, the first thing that I typically view is, do I have an alternate solution for glassware or for Xray tubes, and knowing what the life expectancy is of a tube on a given product and knowing its cost. So that's 70% of my decision-making process with regards to an enablement of whether I should service that product or not. Other parts like the Xray generator parts, high voltage tanks, and the computers weigh in about 20% because of the cost and the impact. They're not as high failure with regards to a cost perspective, but they do fail. But the impact to the service contract pricing is a little bit lower. Then obviously consumables that we would have like brushes, those kind of things, and the hours used in those PMs is about 10% of the decision-making process, at least in my view. But the biggest enabler to allow me to do service is obviously training. Training can also impact my cost with regards to how many parts I order, how many parts are consumed in troubleshooting, and the amount of time. So training can reduce my downtime by the FE accurately assessing what the problem is the first time and ordering the right parts for it. And at the same time, that directly impacts customer downtime. And in the case of CT, trauma center ratings as well. So I've had the fortunate in my career to have worked with Dunley on a number of different tube projects, even on the Lightspeed and Brightspeed tubes with the DA200 introduction in the early 2000s. And then later on, the release of the DX240G used on Lightspeed Pro, VCT, and RT systems. And then later on for the Optimus 660 CT, where we have the DA200 P40. That's a ball bearing based tube. And then later on, GE moved into using a liquid bearing tube, LMB. And so Dunley followed suit with developing that tube for the Revolution EVO and for the second version of the Optimus 660, which shipped with liquid bearing tubes. So now that we have the liquid bearing tube, we now have ability to have a lower cost to serve using this tube and improve the customer's choice for service with regards to a Revolution EVO or second gen Optimus 660. So having this glassware available is obviously an enabler for service. So one of the advantages of using a liquid bearing tube is it should increase tube life of the tube because the ball bearings are no longer ball bearings, but liquid metal, which has a quieter and tighter tolerances for smoother operation. In this case, Dunley calls it Cool Glide, that reduces the friction, and so tube life should be extended due to bearing failure. And obviously an enabler for the GE Revolution EVO product and the Optimus 660 products as well. Yes, with regards to Xray tubes, AllParts would be a good source for your Xray tubes with the Dunley brand. New Phillips and Dunley tubes, which come with full manufacturer warranties. Also certified pre-owned Phillips and Dunley tubes, as well as a large selection of pre-owned tubes for multiple manufacturers. And with that comes 24/7 sales and technical support assistance for our customers for both pre and post sales. So I'll give you a minute to look at the slide, and then we'll move on to the next slide. And then finally, realize that AllParts, not only do they do parts in harvest, but repair operations has QA bays to validate testing, image quality on parts that are repaired. So these systems are also leveraged for training. In the GE space, we have the Revolution EVO product, Optimus 660, Brightspeed 16, two Lightspeed VCTs, one with the older VDAS, one with the newer HDAS. And then we have the 5X HP60 system, the 5X Pro 16100 for high power Xray generators, and then an older Lightspeed 4X system. That product was released in 2002. So quite a few, 19 years ago to be exact now. So there's a spread of systems in the GE space. And then Siemens, we have the Emotion 16. We also now, not included on the slide, is Perspective 64, which was based on the Emotion 16 design as a newer product. And then we have the Sensation 64, and then the Definition 128. So obviously there's variations within these platforms, like the Definition AS, there was a 40 slice version, 64 slice version, and the 128, and other versions as well. So realize that these systems allow us to test parts for derivatives of these systems as well. So AllParts has a search page to be able to look for parts with regards to CT and other modalities as well. So here's the URL for that. And then our training, as we talked about before, training is an enabler for service just as well as having parts availability in classwork. So here we have examples of a GE training course. That course allows us to train on a large variety of systems that are based on the newer 5X platform all the way to the Revolution EVO. The reason why we could do that is, one is we have a number of bays that we allow the students to be on. We use 3 bays during training, a 5X platform, a Brightspeed platform, and a VCT, and obviously Optimus 660/Revolution EVO access as well. So we have a number of systems. GE was pretty much consistent in one design topology with regards to their products. So the user interface for service tools is highly repeatable as well for all these products. So engineers are giving, typically we have a class of 4 to 6 students based on the year. And with we would have a class size, our troubleshooting size lab group of 2 men per lab group. So if you think we have 3 systems, we can run 3 concurrent lab groups at the same time in the GE platforms. And then we have a difference course, but small differences of the prior generation of 1X to 4X, light speeds that were based on some different control topology. And that course is 3 days long to go back and troubleshoot on the Lightspeed 4X that we have here at the AllParts office. We also have Siemens Emotion training, and that includes introduction to Perspective 64s as well. That's a 10-day course, and then we have a 9-day course for the Sensation 10, 16, 64 system, and then a 9-day course for the Definition AS product line as well. So now we're open for Q&A. If you have any questions, just please address them, and I'd like to answer them as soon as possible.
Thank you, James, for a great presentation. As a reminder to the audience, if you have a question, please use the questions feature on the webinar dashboard, and we'll get through as many questions as we can. We'll start with the questions that have come in already. James, I don't know if you can go back to your slide that has the contact information on it so anyone can jot that down if they need. Thank you. Our first question is, how have any of the major components in CT scanners changed over the years?
Well, realistically, with the history that I have, is originally the first CT scanners would do 1 full rotation in about almost 10 seconds. So that's down to about a half second now. Also, there were high voltage cables in the back of the gantry, and you could do rotation, but not full 360 rotation all the time in one direction. So we have had consolidation, newer technologies, computers, everything got integrated, more and more hardware. We used to have separate rooms for the computer, for the X-ray generator, all those elements. Now it's all condensed into basically a very few components that actually are the CT platform. Other than the console, everything else can be in the CT scanner room now. So a lot of large consolidation. For instance, the DAS detector boards, originally they were designed with regards to having a long wire length from the back of the detector to the A to D, and then obviously the conversion process. You could pick up stray noise, those kind of things with those wires. All that's been shortened, where actually the A to D is on the back of the detector module now, and so much faster in acquisition time, also lower noise and more integration. So a board chassis may have had 5 or 6 boards in it, unlike the 8800 that I first started with. Now that's down into maybe half a board, where the other half may even have other functions now. So everything's integrated on one board. So, and then computer power as well. With regards to the first computer I worked on was Data General S200, and that ran at about 16 megahertz. Now we're dealing with computers that are operating in the gigahertz range, and parallel processing, newer operating systems. So a lot of consolidation, a lot of improvement. So it's been ever evolving, even into now adding AI and other functions as well into the CT products to do better image analysis.
Our next question is, where can I find a list of all of your training courses available?
That would be on the AllParts website under training. That training, we currently have the posted schedule for 2021 up, and then later this fall, sometime around right after probably the end of not first quarter, but beginning of fourth quarter, the update for the 2022 sessions will be up there as well.
How do I get a quote on one of the new Dunleavy liquid metal bearing tubes?
That would be calling the AllParts number that will be part of this package that you could go back and review. Any of the sales specialists can then do a quote for a new Xray tube.
In addition to the CT tube, do you also provide parts for the newer GE Revolution Evo and Optima scanners?
Well, that would be the DA200 P40 Plus liquid bearing tube. So that tube was just released at RSNA last year. Again, I said it's a newer enabler. A lot of those GE systems are now at the end of 5-year service contracts. Usually at point of sale, they would have been sold with a service contract. So we're seeing a lot of those systems come to market now in the third-party space. So AllParts, not only do we have a QA bay for those systems, we also have parted out a number of systems for parts. So not only for the Xray tubes, even used tubes, but we also have all the other detector components and computers parts as well.
This one, I believe, references pretty early on in your presentation. The question is, the lungs are kept moving. The images are very clear. How is it possible to see these clear images while the lung is moving?
A great question. Originally, it was a problem in early CTs when like an 80-100 would took almost 10 seconds, 9.8 seconds to do a full 360. And patients are asked to hold their breath during the acquisition time, but realize that when you're doing one slice to the next in axial mode, that would take a very long time. Now with multi-row detectors and asking the patient to hold a breath, which only realistically they have to do for any time, maybe 1 to 2 seconds full. It's much easier to do to have that anatomy stabilized while you're acquiring the image. You can still get motion artifacts, but the techs can real quickly rescan the patient and to get that. But yes, movement has been a problem early on in early CT in the 80s. That's one of the reasons why gantries now spin much faster than they used to. Like earlier scanners would do almost 10 seconds, then it got down to 4 seconds. Now we're down to half second and even less time when we're doing gated heart studies. Okay, great question.
All right, our next one is, other than not using it, is there anything users can do to extend the life of their tube?
There's a couple of things that happen with tubes, right? It's all dependent on how the customer uses them. This becomes a challenge. Every site is a little unique. We've seen sites where they do trauma ER scanning, and those tubes seem to last a very long time. And then other sites that are low usage actually consume Xray tubes sooner. Part of it has to do with thermal cycling. And if we get a tube up to a certain temperature and it operates at that temperature consistently all day long, how many thermal cycles has it endured? Realistically, not a lot. It's gotten hotter and colder as being used, but there's a lot of cooling capability in the gantry as well to try to dissipate that heat as much as possible. Whereas if you scan a couple of patients and then the tube cools down and then you scan a few more patients and it warms up, we're going to deep thermal cycling. So it used to be when we had just conventional bulbs instead of LED bulbs, when would a light bulb fail? Sometimes when we were just turning it on. That current rush through the tube would actually cause a filament failure. That is still one mode of a tube failure. with regards to a lot of CT scanners, especially the GE product line and some others. They use dual filament tubes. There's a small filament for better resolution and a larger filament used for some of the body studies. 70% of the time, that small filament's being used most of the time of the studies. So that filament's typically the one we see fail the quickest in a lot of cases with tubes as well as they age out. But thermocycling typically is the biggest challenge with extending tube life. So one of the things we can do as tubes get older, if they're a conventional tube design, one of the things we can do is on the G systems, we have a tool called hot ISO, where you go in and it actually heats the tube up. It uses low techniques, but gets a lot of heat on the tube, stabilizes it, and the graphite can then absorb some of the stray gas floating around in the insert to extend its life a little bit as well. That's what we do on some mid-tier usage sites and low usage sites, is try to extend the tubes in that way as well. Good question.
Our next question is, when switching from a GE OEM tube to a Dunley, is there a weight difference requiring the gantry to be rebalanced?
It's always a possibility, but my experience and also working with the Dunley development team was to ensure the tubes match the weight of the tube, and so it would be minimal. Even when you replace a high voltage tank or any component on the gantry, if it's not exactly where it was before, there could be a slight imbalance. So these scanners typically scan every day to validate balance before they are used during some of the air calibration process. So they're designed to equal the manufacturer's tube weight, but at the same instance, if you're at the edge and you've moved other components like troubleshot with a high voltage generator or something like that, it might be that you still have to deal with the gantry balance. It's actually part of the procedures on these scanners to verify gantry balance as well, just because it can happen with other components too.
Thank you again, James, for your time today and for a great presentation. I'd like to encourage everyone to visit today's sponsor to learn more about the services they provide to our industry. Please visit allpartsmedical.com. A quick reminder that you can obtain your CE certificate by completing the post-webinar survey. The survey will be emailed 1 hour after the end of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI. You'll be able to download your certificate immediately following the submission of the survey. If you have any questions, you can reach us at webinar@mdpublishing.com. We'll be back next week with another webinar. Please visit webinarwednesday.live for more details and complimentary registration. Thank you all and have a great day.
Thank you.